Let's think about how we can use the second derivative to justify the existence of local extrema of a function. So how can I use the concavity of a function to talk about a local maximum or a local minimum? Right, recall that if you're a extrema of a function, if you're a maximum or a minimum, it can't be when your derivative is non-zero, because that means that you're increasing or you're decreasing. But either way, if you're increasing, then your maximum is not right there, right? It's further to the right because you're increasing. Same thing, if you're decreasing at a point, then that means you're not an extremum because you're decreasing. Your taller values there, you've got smaller values there. Right? The only way that you can be a local extrema of a function is at what's known as critical points when the first derivative is equal to zero. Right, there we have horizontal tangent lines or hilltops or valleys, or where the first derivative does not exist. Right? You could be a sharp turn and be a maximum. You could be the endpoint of an interval. So if the function doesn't exist over here, then there's no way that you can construct tangent lines. Or maybe you've got something like this going on, right? So there you actually do have a maximum. In fact, all three of these places you have local maximums, but the first derivative does not exist there. But if we want to use the second derivative to justify the existence of a local extrema, then that automatically throws away all of these cases, because if your first derivative doesn't exist at a point, then there's no way that the second derivative does, right? Just like the first derivative can't exist where the original function doesn't exist. If the first derivative does not exist, then the second derivative can't exist either. So we can use the second derivative to identify maximums because we'll be concave down, or minimums because we'll be concave up. So let's do that here. Let's take this function f of x. All right, and before we differentiate this, I think I want to rewrite it. We've got x cubed. Let me factor out an x there. And I believe that denominator factors. Oh, sorry, that should be a 1. That denominator is going to factor as x minus 3, x plus 1. Yeah, it's a good thing that we factored this because I think we get cancellation. We can simplify our function a little bit. That's going to simplify when we take the derivative. All right, those are gone. We now have x times x minus 1 over x minus 3. Okay, let's write that as x squared minus x over x minus 3. So we don't have a product rule in the numerator of our quotient rule, because now we are ready to differentiate. The first derivative is, we're going to use a quotient rule. So low d high minus high d low, that's just 1, all over low low. All right, let's clean this up. 2x squared, what's that going to be? Minus 6x, and then minus an x, so minus 7x. And then minus 3 times the minus 1 gives me a plus 3. You have minus x squared plus an x over x minus 3 squared. That's going to be 2x squared minus x squared is just 1x squared. Minus 7x plus x is minus 6x and plus 3 over x minus 3 squared. Does that numerator factor? Two things to multiply to give me 3 and add to give me 6? No. Okay. So our first derivative, our extremums can happen when this first derivative is equal to 0 or does not exist. So let's do the does not exist part first. because that's easy. You're not going to exist when you divide by 0. So that's when x is equal to 3. So the only place our first derivative does not exist is where our original function doesn't exist. Oh, and also at -1, because our original function does not exist there either. Okay, let's think about zeros. So what's going to make x squared minus 6x plus 3 equal to 0? So I think we've got what? Let's use a quadratic formula here. Opposite b plus or minus square root b squared minus 4 times a is still 4 times c is 12. All over 2 times the a, that was a 1, so that's just a 2. Okay, we've got 3 plus or minus 1/2, distributing that division by 2. 36 minus 12, what is that? 26, 24. Okay, so square root 24 isn't going to give us a nice answer, but as a decimal approximation, we get 3 plus 1/2 square root 24, 5.449 roughly. All right, so in fact, I don't want to say equals at this point. This is now us approximating. The other 0, 3 minus 0.5 square root 24 is about 0.551. Okay, so let's see. I know I don't have a extremum at x is equal to 3 because my function doesn't even exist there. And the function asks me, show that it has a local maximum and a local minimum. So let's figure out which one of these is a local maximum, which one is a local minimum. And let's use the second derivative to do that. The second derivative is going to be low d high minus high d low all over low low. Okay, now we really don't have to simplify this any. You can if you want to. It's going to make the evaluation simpler. But we just need to see what our second derivative is doing at these 2 points. So if we plug in 5.449 into this second derivative, we're going to get something about 0.82. That's a positive number. So we're concave up, or sorry, we're concave, yeah, concave up. But that means that we're going to have a local minimum there. So at 5.449, we have a local minimum. And our second derivative at 0.551, the other critical point, oops, I don't want to say equals because we've already approximated here. The approximation is about minus 0.81. It's negative, we're concave down, which means that we're going to have a maximum. So this point right here at 0.551, that's going to give us a local maximum.